Yeah, hi. Good evening. Happy to be here. Thank you for coming. I'm surprised we have a good number. I didn't expect so many people coming up. Thank you. So let me start off the presentation with a question. So as you see the question here, are containers secure? What do you guys think? Do you think containers are secure? How many people say containers are secure? Just one person? Okay, another person? Yeah, why do you think containers are secure?
Yeah, it's that they take advantage of privileges and you don't give them privileged access, then if it's not secure, then there's development.
Okay, yeah, that sounds good. Yeah, so it's all about privileged access. So today we would like to explore this aspect of the containers and also understand what is proposed here in this presentation. So the title of the presentation, as we say, Fast and Secure Containers on OpenStack, a Winner. So we wanted to propose something which is not been done before in the industry, and we also wanted to say that containers can be made secure. So this is the theme of this presentation, and also maintain the speed of the containers as we have been known to know them. Okay, here is the speaker profile. I'm Surya Naredla, and I work for Dell EMC, and she's my co-presenter. I'll let her introduce.
Hi everybody, I'm Madhuri Kumari working with Intel. I am mostly contributing to Zun, the container related project, so I'm a co-reviewer currently with Magnum and Zun project.
Yeah, thank you. So in this session, here is a brief agenda. We have a proposed solution, then we'll look into the architecture of the solution that we are proposing here. We'll explore this with a use case. So let's see, we take a use case of a container, and let's understand how secure it is in a normal environment, and understand the problems with it, and then explore the solution and see how it is going to secure the containers. And then we'll go into the implementation of this solution into OpenStack, and at the end we'll see a demo, and if time permits, we'll take some questions. So, yeah. So just remember this date, October 2016. This is the date when we had this CVE, that's the vulnerability, kernel vulnerability called as 2016-5195. It's also called as, dirty cow. Dirty cow is a kernel vulnerability which was in the Linux since 2007, in the Linux kernel since 2007. So this is an exploit which has been found out, and kind of a patch has come up inside the kernel, but this pretty much affects every Linux kernel out there which hasn't been patched. So let's understand this kernel vulnerability and how this is going to affect our scenario here. We're using containers on a kernel which is not secure here. So the typical vulnerability is about copy and write, where if you keep writing, if you keep writing multiple pages using copy and write, and at the same time cleaning them up, and if you do this in a very fast cycle, what happens is there comes a race condition wherein you start writing into pages which are protected. So typically a read-only page can be written in when you do this at a very fast pace. So there are multiple vulnerability rootkits which have been on the internet to exploit this bug. Now how this is going to work? This is our scenario where we are using Docker with the Linux kernel which is buggy, okay? And we have multiple containers, container A, B, C. Let's assume each of these containers belong to different customers. And a user who's logged into a container A, this one, and he tries to exploit this bug. He doesn't need to be root. He just needs to be a normal user. And he implements this vulnerability inside this container, okay? And let's say if there is a mounted file system here, which is a read-only mounted file system, which is passed as data to the container, with this copy and write dirty cow vulnerability, he's able to start writing into read-only areas. So this and with the help of that vulnerability, he would be able to access areas which are not supposed to be written by a normal user, let alone root. Okay, so this vulnerability affects almost every Linux kernel out there. And let's say if you run multiple containers with these kind of vulnerabilities, you can definitely affect parallel containers which are running. Now, typically containers, the security around containers is you build them, you kind of secure them, you sign the images, etc., and try to secure them. But what about zero-day kernel bugs? A bug can come today, and you might not even know for a long time. Like the dirty cow, for example, it's been 10 years since the patch came in. So what about zero-day kernel bugs? So the point here is the security should be built runtime, not during the build phases or signing the images. They are all mitigations, but when the bugs come in on the fly, you should have some sort of a solution which helps you, protect it during the runtime. That kind of security is needed. So in this scenario, we understood that this is a problem. So let's move into what we are proposing here. So next one. So the concept here is clear containers by Intel. So these are hardware-backed containers. Hardware-backed in the sense, like, let's say if you have a virtual machine that you're running on Intel architecture, you get hardware-level protection with the virtualization flags, the VTD flags. Okay, so each of these individual virtual machines have their own isolated environment, and typically they won't be able to step out of their isolated environment. They have their own kernel address space and their memory, and and things like that. So why not use the same concept of getting hardware-level protection to the containers while keeping the agility? That's the point. Optimize container in such a way that you get the same execution flow, the speed, agility, and efficiency while getting protection from the hardware. This has been there for a very, very long time. Everybody trusts virtual machines today because of their capability that comes from within the hardware. So why don't we take the same functionality and give it to the containers? That's the whole point here. So clear containers achieves that, basically. And clear containers is already officially supported in all these platforms, including Microsoft Azure, Kubernetes, Docker, Swarm, everywhere. And multiple Linux distributions are supported. CentOS, Fedora, Clear Linux, Ubuntu, all these distributions are already supported. So it's just a matter of time that we start utilizing this feature into native cloud. So next page, please. So here is the architecture of the clear containers. Let's get into the details here. So this is the host's user space. Let's consider this as a whole machine. This is the user space. This is the kernel, and this is the clear container environment. As you can see, we are using a component called as QEMU-Lite. QEMU is something which we have known. Okay, QEMU is the user space utility which spins up virtual machines for us in Linux. And it uses a kernel module called KVM. And KVM goes and talks to VTD features to get the isolation that we needed, right? So clear containers have come up with something called as optimized version of QEMU, also called as QEMU-Lite. Typically, when you boot a virtual machine, you have various steps. One is initialization of hardware, then the BIOS boot up, then the kernel boot up, initialization of hardware inside the kernel, and the entire memory footprint takes huge amount of resources. And that's the reason you see virtual machines are getting delayed in terms of booting up. They are not that fast. Containers don't have this problem typically. You just boot the kernel directly in the containers and bring up your user space and applications within the container. So that's the advantage we have with containers. So here what we are proposing is using a module called as QEMU-Lite, which has been very well optimized. The BIOS boot up, the boot up has been reduced pretty much. The memory footprint is under 670 MB or something. And it uses a customized Clear Linux OS, which has been optimized to boot on these kind of environment. So basically, when you spin up clear containers, instead of seeing a binary called QEMU, you would see a binary called as QEMU-Lite, which would internally call the Clear Linux OS, and this CC Mini is the Clear Linux OS, which I'm talking about. So it uses the same KVM kernel module, no difference about that, and then boots up the container. Uh, so th- so this whole boot up is less than 500 milliseconds, which is pretty comparable to what we have on regular containers. Pretty comparable. But as you know, virtual machines take way more time to boot up. Next slide, please. So using the same example, this is our previous use case where we have multiple containers being used by multiple customers. And we have this VTX security measures for each container. So each of these containers is having a cumulate underneath, okay? And is directly talking to the kernel using KVM. So this is exactly like how you're going to do virtual machines. No difference, but with all the advantages of speed and low memory footprint. So each container sees its own isolated protected unit, and then they boot inside that box. So basically, you have all the advantages of hardware virtualization plus the speed. So this is the case. This is also called as this runtime is called as COR, the clear containers runtime. So just to summarize on the advantages here, if you see a virtual machine, we have a slow boot problem, and then the management is pretty heavy. We need to use libvirt and other tools, and we have excellent amount of security measures in that. If you see a container, it's extremely fast in its booting, and then it's kind of easy management with Docker kind of tools, but we don't have security. That's the issue here. Of course, we get the performance out of it because we're just sharing the host features here. So to strike a balance there is where clear container comes in. You get the rapid start, pretty much as close to as what we get on containers, but not exactly same. The management is pretty easy, and you get the security. So this is what is the major issue with containers, and that's what is being solved with the help of the features, hardware isolation features here. So going forward, bringing this feature into OpenStack makes a lot of sense for us. Okay, already it's been implemented by public clouds, and then getting this feature into OpenStack makes a lot of sense. It's pretty easy to implement it, and we already have container services which are calling regular containers like Zun and Magnum. So adding this feature would make a lot of sense. So this whole slides coming forward are going to be about how it has been implemented into OpenStack, and my colleague will take it forward.
Okay. Thank you, Surya, for such a nice explanation of clear container. So now that Surya has already talked about the advantages of having clear container, which is secure and not as fast as containers, but it has a similar optimized performance as compared to containers. So there is a progression of supporting it in OpenStack. So I will briefly talk about how does OpenStack ecosystem look like, and where are the projects where we can integrate clear container today with. So as you can see that this is the OpenStack ecosystem, and we have all the virtualization techniques running at the compute host. So it may be the COEs, the container runtime engine, and the libvirt for different compute services. So let's say, for example, Nova uses this libvirt for creating the VM, and then Zun uses the container runtime tools to create containers, and Magnum uses the COE to boot up a container cluster on top of OpenStack ecosystem. So, and there are also other projects which support this project, like images, we can get it from Glance, and Cinder provides the volume for us. And okay, so can you go back to the slide? No problem. Okay, so that's how this is the OpenStack ecosystem. So we have mainly two projects where we try to integrate clear container with. So the first project is the Zun, which we have a basic support now, and the second project which we target is Magnum. So Magnum has the COE clusters where we can directly integrate this clear container as a separate runtime available to these clusters. So that is not yet done. We will be doing it after we do it in Zun. So in the next slide, I'll be talking about how we did it in Zun, what is Zun all about, and we'll show a demo of running clear containers with a regular container in Zun. So before that, I'll just like to explain what Zun is. And so Zun is the container management service for OpenStack. So it lets you run your container on top of OpenStack ecosystem. So it supports Docker for running containers. So Zune is extendable in sense it can support other runtime tools as well. You just have to implement a driver for other runtime tools like maybe Rocket in future, and then you can have support for other runtime tool as well. And we propose to actually integrate with all the existing solution to use the advantage of this project rather than reinventing the wheel. So we have integrated with various projects like Keystone for the basic authentication purpose, and Neutron, and not Neutron directly, but we are using Courier Lib Network for providing the network for our container resources, Glance for storing the container images, and we do have a UI for Zune, which users can use to create containers very easily. And then we have integration with Heat, like container, Zune does not do any orchestration of container. So you can use Heat to do the orchestration, like you can write a Heat template and create multiple containers that comprises your application, like a web server and a database server, and then you can run that Heat template and you'll have a set of containers running and have an application. So we have also integrated with OpenStack clients. So we have a standard OpenStack format commands for creating containers and doing some operations on the containers. So these green, the projects marked in green are the one that we have already implemented the integration with, and the red ones are still like work to be done. So as I have explained, you can see this diagram. What it explains is, you can see the first part is the Nova part. There are Nova instances running, like you can say an application like web server, and the database servers are running on 2 VMs, and they are sitting on the same network. So they have the communication where your applications can communicate and form a complete running application. Whereas in Zune, you can have your applications running on inside containers, and you can even have a mix of a container and a VM. For example, the database services needs more of the hardware requirement for better performance. So we prefer to run it in database, and then the web server can run easily inside a container. So due to the integration with Courier Lib Network, we are able to achieve this kind of approaches on OpenStack, where you can run 2 applications on a VM and a container, and they can communicate over the network. So, okay, so now that we have seen what basic Zune is, we can now see that this is the workflow, and we have 2 most important components in Zune. One is called the Zune API, and the other is the Zune Compute Service. So the Zune API is the user-facing service. It accepts the API request from the users and pass it to the Zune Compute. Zune Compute does some processing. So let's take an example, like a user says, I want to create a container with Zune. So he will send a request to the Zune API to create the container. So the slide changed, okay. To create the container, Zune API will authenticate the request with the keystone, check it for the action, whether he is allowed to perform such operation or not. If he is permitted, the request will be forwarded to the Zune Compute. The Zune Compute will then talk to Docker, download the image, create the network, talk to Courier to create the network, store the image in Glance, and then finally submits the request to Docker to create the container for us. So there are some calls which are async based on the time of operation it takes, like create takes a time for downloading image and then creating the container. So that is an async call, and there are other calls like killing a container, stopping a container. Those are sync calls based on the time they take. So this is the general workflow which we have in Zune. So now we will see how Zune and Clear Container works together, and where we have integrated the CC runtime with Zune. So as Surya has already told that Docker has this option for running multiple containers, like multiple runtimes. These runtimes are pluggable. You just have to specify the runtime which you want to run your containers with. So by default, that is runc, and you can add another runtime as just say this is the command. For example, this zone run -- runtime COR. COR is the clear container runtime which we are going to create our container with. And then the name of container, image which we want our application to run with, and then the command. So here you can see that we have a driver concept in Zone, like Zone is extendable and trying to be include every kind of tools it can support. So it has a driver for Docker, and this driver Docker has parameters which it accepts to pass it to Docker. So as I've said that this runtime parameter is just an option to the Docker command. We pass this option to Docker, and Docker handles and forwards the request to the CC runtime engine, and CC then handles the creation of clear container for us. So now we'll see how we have implemented this clear container in Zone, and what we have done so far, and what are the things we need to do. So the first thing is like regular containers should not coexist with KVM and clear containers due to the security reasons. As Surya has given some examples as well, that the regular containers are not secure. So we propose not to run a clear container and a VM and a regular container on the same host. So for that, we propose to, I can give an example here, like the banking sectors, they need more secure clusters for running their operations. So we can hide the complexity behind and say one compute host just runs clear container and the other host runs the regular container. That way, even if the regular container compromises our host kernel, our clear containers are safe. It is not going to be affected by the other operations. So that way, we propose not to run both type of containers on same host. So, and similarly, we allow admins to restrict a project or a tenant with a specific list of runtime. So we create a project and we say this project can only support clear container or runtime, or there could be some scenarios where they would want to run clear container and a regular container on the same host. So we do have option for that, but it is restricted to admin, just for adding an extra layer of security. Non-admins users should not be allowed to switch runtimes other than the allowed list. Yes, so of course, when the nodes are tagged, we have a list of runtime which a host can support. A non-admin user is not allowed to pass that list and choose any other list of runtimes. Otherwise, it would be a security concern. So we propose to do this in Zone as well. Finally, for achieving all these 3 steps, we will be tagging nodes with the runtime it supports, or maybe in future we would have a similar concept of having a zone where nodes are tagged with the type of runtime it supports, and for when a user requests for running a clear container or a regular runtime container, it will land on the zone where that runtime is supported, and the container will be residing on one of the hosts. So after talking all about this clear container in Zone, how is it possible for you guys to run clear container today with Zone? So it is as simple as adding this enable clear container equals to true in your DevStack configuration file. This is now work in progress. So this will set up a DevStack. It will do all the setup for you, and you can run a regular container and a clear container with Zone. So now we'll be showing a demo where we will be creating a regular container and a clear container with Zone. And this is the development environment. So we'll be running clear container and regular container on the same host. So we will see that we don't have any containers here in the zone list. So we'll just check for the zone list and the Docker command to see whether we had any containers created before we created the demo containers. So we see that there are no containers, and in the next step, we are creating a regular container. By default, the runtime supported by Zun is runc. So we are not providing any runtime here. So it means it will create a runc container. So that we will see in the next step. So as you can see here, the status is creating, and the parameters is none now, because I have already told that this is a async call. So it will get populated once the request is submitted to Zun compute and the response returned to the user. After the request is actually processed by Docker and it is updated in the database. So now, after creating the runc container, you can see the Docker ps command shows a new container which we created. The image was zeros and the command was ping Google DNS. So the container is now running, as you can see. So in the next step, we are going to see what was the runtime for this container. So you can see here the runtime is runc for the regular container. This is by default. Okay, so for using clear container with Docker, you have to do some configuration like install clear container and then configure a new runtime for the Docker. So all that will be done by setting up with DevStack, or else you have to do all this step manually and configure Docker to use clear container as one of the available option for runtimes. You can see here that the runtime supported are COR and runc. COR is the clear container and runc is the regular container, and by default it is runc. So you can see here that we are using another CLI. This is CCOCI runtime list. This is the CLI to talk to the clear container engine. So we see that there are no containers, and now we will use Zun CLI to create a clear container. Okay, so before that, we'll see that, as Surya told you, that clear container uses QEMU-Lite. So we can see that there are no containers running with QEMU-Lite. So we are going to create a new container, clear container with Zun, and see that it will be available after the container was created. So I have specified the runtime COR here. This is the clear container runtime. So it will create a clear container for us. You can see the runtime here is COR because we specified it in the command line. We'll see the status of container now. So we should have two containers, one the regular container and the other clear container. So yeah, you can see the runc and the clear container both are running. We'll go check the Docker and the CCOCI list as well. Yeah, you can see now we have two containers. The first one is the regular container and the second one is the clear container. And we will again see run the CCI list command. So we see that one container is created with the container runtime engine, and we will also see the QEMU-Lite example here. Yeah, so this should show. Yeah, you can see here that the QEMU-Lite has created a clear container for us, and this is the clear container which we created from Zun. So in the next step, we will just stop the container, delete the container, again check that the container does not exist with the clear container runtime.
So we're almost out of time. If
you
have any questions.
So I think we can skip the next part. This is just clean.
So it's just cleaning up the containers.
Yes. The next step just cleans up the clear container and check whether it exists with the clear container or not. So this is just cleaning up the containers. So We are done with our presentation. Any questions are welcome. We would be happy to answer any questions.
There's a question there. Yeah.
What is the impact in terms of memory and performance when running under clear containers?
Sorry, I cannot hear your question. Can you?
So what is the impact in terms of performance and the memory request when using clear containers?
Yes.
What is the impact of memory?
And performance.
Yeah, so on the Intel side, there's a PDF which clearly mentions about the amount of boot memory it takes, but it's way lesser. It's around 70 MB something, the initial usage of memory. It's way lesser than a regular VM. Yeah.
Performance, CPU performance?
The CPU performance inside the container, right? You can actually pass the parameters to Docker to give how many CPUs you want to pass, etc. And it would be exactly like how you would see in a VM. There would be no difference in the performance. But the only thing is that the boot is optimized. The way the containers come up are pretty fast. So that's one of the biggest advantages we have. Any more questions? Yeah?
Can we use the Docker image directly on Docker?
Yeah, so let me rephrase.
Yes.
Can we use Docker image directly?
Yes.
Yeah, the Docker image can be used directly, but the only thing is the kernel that is inside the image should be a clear Linux OS kernel, because the kernels are optimized to boot faster. Typically, if you take a normal kernel, it has a lot of hardware initializations. For example, a regular VM might use a C BIOS or some other BIOS format, so you have ton of hardware initialization. You wouldn't do all that. So the kernel is called as clear Linux kernel, and it should be inside the image, or those optimizations should be present.
No, you are talking about the container images that is used to run. Yeah, that is the same container image you use with Docker. There is no change. Yes. Yeah.
We can allow benchmarking between the clear container and Docker and
Yes.
memory similar solutions.
Yes.
And we found out that clear container there are no overhead, almost no overhead to the CPU and the memory. But we found out there is huge overhead of the networking.
Okay.
Do you recognize this? You will show the half of the performance from the Docker.
Okay.
Compared to now one quarter of the performance and then comparing to the Docker.
Yes. Yeah, so his question is like, there is a performance degrade using clear container as compared of using regular container. Yes, there is a performance degrade when you use clear container, but when you compare it to the VM, the performance is really fast, and there is a trade-off between the security you get with VM and the performance you get with containers.
We have a both VM as well, so when we run comparison between the VM performance and the VM performance, we usually do that. Some percent overhead is there, but clear container and Docker there is much more overhead. So do you recognize this?
Yes, there is a
Overhead is much more than comparing to the other.
other containers, you mean?
I mean, pure VM, and then there is probably there is performance overhead between the pure VM, pure PM, right? Which comes 준비하면 더.
Yes.
And some benchmark, well, just the network benchmark between the virtual machine and the VM. There is almost a 30% gap between them, but comparing the running Docker and the clear container, it shows that almost 75 differences. 75 differences.
Okay, so yeah, I agree to that. So we can, if you are okay with it, we can take this your benchmarking result, and you can always go and ask on the Clear Linux channel. They are very responsive, and they will surely reply to it and check whether there is an issue with the scenario or anything. So you can have those results and go and talk to the Clear Container guys on the Clear Linux channel.
I will just send the email.
Yeah, sure. And even if you want, you can take my contact information and you can contact me. Okay. Yeah.
Okay.
Thank you.
Okay, I think we're out of time. Thank
Yeah.
you so much.
Thank you so much for your time.